Thank you very much for joining us today for our latest webinar titled Beyond the Pump Curve, Practical Design Considerations for Regional Pump Stations. We hope this will be a useful and informative hour for all of you.
Thanks, Chuck. Welcome, everyone. Let's kick off Beyond the Pump Curve, Practical Design Considerations for Regional Pump Stations. So in today's presentation, we'll walk through some key considerations for both the design of new regional pumping stations as well as the rehabilitation or upgrade of existing regional infrastructure. Paige, Mike, and I all primarily work in the coastal South Carolina area. So though the examples we'll present are specific to the coastal Southeast, the broader objective of this webinar is to highlight a range of design considerations that can be applied in different ways depending on the region you're in, whether a project's located in Florida, Massachusetts, or anywhere in between. We'll begin with some general regional station design considerations and what makes regional stations different. Then we'll move into and discuss common design pitfalls, drawing from real-world lessons learned to help avoid costly issues during design and construction. We'll shift to planning for for effective daily operations, focusing on how design decisions directly impact maintenance, reliability, and long-term operational success. And then from there, we'll cover hydraulic design considerations and pump impacts, including how pump selection, control strategies, and system hydraulics affect overall performance. And we'll close with planning for the future, summarizing what was discussed about designing regional assets that are adaptable, resilient, and capable of meeting future demands.
Pump station design. Oh, sorry, I wasn't unmuted. Today we'll be focusing specifically on regional pump station design. Next slide. Many of the examples we'll walk through are drawn from projects in the Southeast and coastal areas where we often deal with unique challenges like high groundwater, warm temperatures, and extreme wet weather. That said, a lot of the lessons learned and design considerations we'll discuss can be applied more broadly to pump stations across the country. So what do we mean when we say regional pump station? We're generally talking about stations that have one or more of the following characteristics. They receive flow from other upstream pump stations. They typically handle a significant portion of the overall system flow. They are considered critical infrastructure and require near continuous operation, or they deal with more complex hydraulics, such as significant wet weather flow peaks, non-typical diurnal patterns, or force main manifolds upstream or downstream. And to be clear, what we're not talking about here are standard duplex pump stations or small package stations that only serve a single development. With regional pump stations, one of the primary design drivers is maintaining continuous operation and minimizing downtime. In many cases, we approach these stations as extensions of the treatment plant rather than standalone facilities. To achieve that level of reliability, redundancy becomes a key component of the design. For larger stations that are critical to overall system performance, this can include features like dual wet wells, dual on-site generators, and redundant electrical systems. The goal is to allow portions of the station to be taken completely offline for maintenance while the rest of the facility continues to operate safely. For example, dual wet wells provide the ability to isolate one side of the station for cleaning or valve replacement without requiring a full shutdown. From a power standpoint, we typically look for generator capacity that can support complete station operation with a single unit. That way, if there are failures during an emergency, there is still a redundancy built into the system. Similarly, redundant and separated electrical systems allow operators to fully isolate portions of the station. This improves safety during maintenance and can eliminate the need for arc flash protection in certain situations. Overall, the focus is on creating a system that can be maintained and operated reliably under both normal and emergency conditions without interrupting service.
When designing large regional pump stations, construction considerations play a key role in managing costs, schedule, and overall project risk. One strategy, especially for upsizing wet wells if space is available, is to utilize the existing wet well during construction. Doing so can significantly reduce the complexity of bypass pumping and minimize construction risk. In cases where space allows, constructing a new site adjacent to the existing facility while keeping the original wet well in service can be a highly effective approach to reduce downtime and bypass costs. It's also important to consider the surrounding environment and community early in design. Some stations are in remote areas, but others are located near sensitive receptors, such as schools or residential neighborhoods. Construction activities, particularly deliveries, excavation, or sheet piling, may need to be coordinated around traffic patterns, school schedules, or community events. The aerial photo on the slide was a station upgrade that was right next to a high school. And we had to take into account students arriving in the morning and leaving in the afternoon. So deliveries of materials had to work around that schedule. Similarly, noisy excavation and sheet piling operations were coordinated so they wouldn't interfere with any sensitive events such as exams. And though while the contractor ultimately manages the execution, incorporating these considerations into the design early on sets clear expectations and helps ensure smoother coordination during construction. Site constraints and easements should be carefully evaluated as well. Adequate space is needed not only for the final facility, but also for construction staging, such as access roads, material storage, laydown areas, and crew parking. Limited site access can significantly affect constructability cost if not accounted for early. So in the same example of the station next to the school, we seemingly had plenty of space because the site was right next to a parking lot. However, the parking lot quickly becomes full of students' cars and other areas needed to be evaluated for crew parking. And finally, early and thorough site investigation is essential not only for design, but also implications to construction activities. So detailed geotechnical exploration, particularly for groundwater levels and subsurface rock conditions, gives contractors the information needed to plan for dewatering, excavation, or potential blasting. On larger or more complex sites, using multiple borings is recommended to better understand the variability of the subsurface conditions and reduce uncertainty during construction. Overall, integrating construction considerations into the design phase early on leads to more predictable project delivery and fewer surprises in the field.
There are several other design considerations that play a key role in long-term pump station performance. From a hydraulic and operational standpoint, it's important to evaluate both average daily flows and peak flows and how those may change over time. In some cases, that leads to developing a pump phasing plan where capacity is added incrementally as the system grows. For example, with pump impeller changes or with pump switchouts, rather than installing everything up front. Force main design of the station is another consideration. Depending on the length and configuration, pigging access points may be necessary to allow for ongoing maintenance and cleaning. We also often evaluate the use of variable frequency drives, or VFDs, which can provide better flow control across a wider operating range while also offering potential energy savings. On the site side, there are several factors that can significantly impact performance and maintenance. For stations that receive wastewater with a high debris load, bar screening can be an important addition to protect the pumps and reduce maintenance. Providing on-site overflow or equalization storage can also help manage peak wet weather flows and reduce the sanitary sewer overflows. And in southeastern and coastal environments in particular, odor and corrosion control become critical. This often includes both chemical and/or vapor treatment systems and the use of corrosion-resistant materials, which, while a higher upfront cost, can provide significant long-term value compared to more basic station designs. Overall, these considerations help ensure the station performs reliably and remains maintainable over its full service life. Mike, muting.
Thank you. While the design decisions for regional stations are similar to those made for smaller local stations, the larger size and impact makes it even more important to make the critical decisions early in the project to keep our schedule and protect our design budget. Starting off the project with the O&M staff responsible for the station's operation in the room right from the beginning sets us up to provide the best possible design for long-term use. The operators need to be engaged to provide specific input on layout and access for various types of work needed to operate the station. Truck size and configuration, mobile or fixed crane access, and space to make entry into the station are all examples of design decisions that need operator involvement. Similarly, the piping design needs to take into account the operation and maintenance conditions the station will be subject to. In the South Carolina Low Country, we may emphasize easy access to piping, moving the piping and valves above grade, whereas in other parts of the country, the risk of freezing may be a key design driver. The O&M crews are our best resource for making sure that design decisions support operations throughout the station's life cycle. Keeping some common pitfalls in mind as we start our project sets us up for success. In the project planning phase, there are 4 areas that I like to make sure we're thinking about before starting design. These are questions that we need to ask and answer as we move the design forward. First, knowing the surrounding area. Who are the neighbors and what are their key concerns? Both the construction phase and the operational life of the station need to be addressed. Is construction noise or restricted access to neighborhood properties a potential problem? Are there visual standards for the area that need to be met? As an example, one of our stations falls within a neighborhood overlay district dictated by the town. This required us to significantly change our fence design to fit in with the surrounding area. And while it increased our cost, it makes it more visually appealing to the neighbors and less likely to end up with some complaints. Second, space for growth is important. Do we need to accommodate future growth of the station? And is it possible within the current site constraints? If not, how and when can we fix that? The solution looks very different if your regional station is being built in a greenfield area than in a moderately or densely developed area. Third, communication of future plans. It's important to know the flow characteristics over the intended life cycle of the station. Are flow rates or wastewater characteristics likely to change? And how can we plan to make future connections or add needed equipment as they do? And last, avoiding last-minute additions. I like to refer to this as getting the wish list early. It relates to growth and future planning, but it's also related to operational needs and wants. We want to provide the best possible project for our utilities, but we have to remember budget and schedule. By getting all the possible attributes on the table at the outset, we can make informed choices from the start with everyone's buy-in.
One of the most common pitfalls in large pump station design is lack of coordination between disciplines, both on the designer side as well as the owners. On the design engineer side, internal communications can be hectic and require coordination with the prime consultant as well as between individual subdisciplines. When civil, structural, mechanical, and electrical designs are not fully aligned, conflicts can go unnoticed until construction. This can then lead to confusion in the field, change orders, and deviations from the original design intent. To avoid this, it's critical to actively coordinate each design stage, overlaying plans, cross-checking work, and paying close attention to components that impact multiple disciplines, especially less visible elements like underground conduits and structural reinforcing. Another issue that may arise is losing focus of the big picture. Design teams can become overly focused on technical details and inadvertently drift away from the original purpose or goal of the project. It's important to continually reinforce the owner's primary goals, whether that's cost efficiency, long-term reliability, resiliency, operational simplicity, etc., and ensure that design decisions consistently support that objective. Internal coordination on the owner side is just as important and can be just as hectic as coordination within the design team. Key decision makers must be aligned and provide clear, consistent direction to the prime, who then disseminates those directives to the respective design engineers. Misalignment or delayed communication can lead to rework, inefficiencies, and confusion throughout the entire design and construction process, and may lead to an end design that's not what the owner wanted, needed, or had the budget for. Thinking in the 3D, a common design issue in larger pump station design is not fully thinking in 3 dimensions. This is one of my favorite slides because I'm guilty of it. As force main, suction, discharge, and header piping sizes increase, so do the sizes of the associated valves and fittings. And that sounds pretty obvious, but is less so when the design engineer is working in a CAD program where they don't have a good sense of scale compared to other objects. Plotted plans plot flat, so it's not only about fitting all the pieces in a plan layout, but also keeping in mind the vertical clearances and overall spatial requirements. For example, air release valves sit atop high points in the piping, typically with some sort of isolation valve, and can end up 6 or 7 feet high if the pipe is large enough, making them inconvenient to service. Surge relief valves are another example. These valves can get fairly large depending on the anticipated surge flow. The example in the photo is a 24-inch surge valve sitting atop an isolation valve and a 30-inch header. So on paper, it was pretty much drawn as a simple block and a note, when in reality, it's about 12 feet up in the air. We were joking it could be used as an airport beacon. Both designers and end users should also think in the 3D with regards to maintenance and operability. Designers need to think through how equipment will actually be used in the field, such as which side valve operators should be located on to make daily operations more efficient, whether valves are manually or motor operated, and whether there's adequate space for crews to access and remove bolts or components safely. This is a great time to get the owner's O&M folks involved, like Mike said, to provide feedback on what a typical day at the station looks like. In this photo, that's me for scale next to a 36-inch plug valve with a 24-inch gate valve bypass connection on the right. As you can see, that gate valve, if it needs to be used, the O&M crews would need to get up on a ladder and probably spend a lot of energy turning that wheel to open and close the valve. A motor-operated chain wheel or actuator or chain wheel might have been better choices for that particular valve. And these are all considerations that should be thoroughly thought through, whether the header piping is outdoors, such as the Coastal Carolina example shown, or within a building where walls and ceilings are providing additional constraints. It's critical to account for overhead structural beams, ceilings, platforms, and even external elements like trees or power lines if you're located outside, which can create unexpected conflicts if not considered early. A simple but important reminder is to always look up, not just around and below, when coordinating the design. Even with proper coordination, there might still be some close calls, such as this image, and it's a sluice gate stem that just barely fit underneath the overhead crane monorail structure.
At the end of the construction phase, the contractor will be turning over the station to the owner and their crews. Pushing the concept of efficient daily operation from the start of design helps these crews achieve their operational goals as easily as possible. Operational efficiency covers a wide range of design topics. Site access and maneuverability, pump access, and equipment access and protection are all much easier to account for earlier in the project. With site access, the question of whether site access is across owned property or via an easement needs to be addressed. The control available with owned property is better if possible, but if that's not available, clear easement documents and communication are crucial. Making sure that space is available for the equipment used on site seems like an obvious need, but working within the site constraints means that careful planning is needed from the start. It's not enough to fit the equipment in on paper. We need to plan for how it gets to the site and gets set up on site before it's used. It's also important to plan for the worst case scenario as well as the day-to-day. If the area is prone to flooding or has risks of severe weather like blizzards or hurricanes, our plans need to be developed with these emergency scenarios in mind. With respect to pump access, regional stations like we're talking about typically have large pumps, so permanent lifting equipment may provide a better layout than using mobile cranes, but the O&M requirements need to be accounted for. Certified operators and a preventative maintenance program for the equipment may be more difficult for the owner to accommodate than simply bringing in a crane contractor when needed. And last, to discuss equipment protection, planning that equipment protection from weather and daily operations is important to consider as well. Sun shields and rain hats may be sufficient, or a dedicated building or control room may be needed depending on typical weather conditions. Bollards, warning signs, and other physical or visual barriers may also help protect critical equipment from damage as well.
As we move into site makeup and layout, this is where a lot of design decisions really start to come together. At a high level, we need to think through some fundamental questions early on. Is there adequate space for all of the redundant elements we've discussed? Are there clear and accessible bypass connection points? Where will the bypass pumps be located, and how do we protect them from damage? From there, the layout really needs to be optimized across a few key areas. First is site constraints. What are the physical limitations of the site? That includes things like providing adequate access and maneuverability for Vector trucks, maintaining safe and efficient access to the wet well, and planning for pump removal. Are you relying on a permanent overhead crane structure, or will you need boom truck access, like Mike mentioned? Those decisions directly impact layout. Next is hydraulics. If an inline flow meter is being used, sufficient upstream and or downstream straight pipe is often required, which can become significant space considerations with larger diameter piping. In addition, fittings and valves can quickly consume space as pipe sizes increase. Operator usability is another major consideration. What does day-to-day and weekly maintenance look like, and how can the site be laid out to support it? Simple elements like permanent access platforms or step stools, as shown here, can significantly improve safety and efficiency. And finally, something that's often overlooked, lighting. Proper site lighting is critical for both safety and maintainability, especially for facilities that may be accessed at all hours. Taken together, a well thought out layout not only improves performance, but also makes the station safer and easier to operate over its full life cycle. That's me. Hold on. Another key consideration in regional pump station design is safety and emergency operations. Because these stations are critical infrastructure, they need to have reliable performance while also being safe to operate and maintain. From an operations standpoint, the focus is on creating a safe working environment. That includes providing proper access platforms, minimizing trip and fall hazards, and evaluating confined space areas like wet wells and valve vaults. On the emergency response side, we're thinking about how the station performs during extreme conditions. This includes having reliable communication systems in place, ensuring the station can maintain operation during an event, and providing safe access to the site when it's needed most. The top photo shows a station that we redesigned that was not technically in a flood zone or floodway, but clearly had flooding issues on site. The generator had been elevated at some point, but all electrical and piping is underwater. Our rehab design accounted for resiliency during a flood event. The station is able to maintain operation by means of the elevated electrical platform, and we limited unwanted I&I through the elevated wet well top slab and watertight manhole covers. Ultimately, these considerations help ensure the station is not only resilient, but also safe and practical for operators under both normal and emergency conditions.
While planning for effective daily operations ensures efficiency in station layout, it must be supported by sound technical design. We'll now shift into some general hydraulic considerations that may influence pump selection, wet well design, and system sizing. Regional stations require careful consideration between hydraulic design, equipment selection, and the electrical systems put in place. The number of pumps is a key early decision. Fewer pumps reduce maintenance complexity, but higher regional flows often require moving from duplex to tri or quadplex configurations. In some cases, using pumps of different sizes improves efficiency across fluctuating flows. All design decisions should align with observed flow patterns as well as owner preferences. Decisions often depend on how the station performs under wet weather versus dry weather conditions, how lead and lag pumps are assigned, and whether the station uses soft starts or variable frequency drives. Reliable flow monitoring is strongly recommended to support these strategies before design begins if you suspect the station receives fluctuating inflow. The layout shown on the slide is a wet pit submersible station with dual wet wells for redundancy, a theme that's been pretty common in this presentation. Each wet well half contains one smaller dry weather pump and two larger wet weather pumps, so 6 pumps total, to meet the varying pumping needs of this particular region. In this example, the dry weather pumps were on soft starts since average daily flows were fairly consistent. The larger wet weather pumps were on variable frequency drives since wet weather flows fluctuate and range from small storm events to hurricanes. An example pump curve for 1, 2, and 3 pumps running on a range of variable frequencies shows how VFDs were used to hit that wide flow design target that was using multiple different size pumps. Electrical limitations related to the pumps can also significantly influence hydraulic design. Designers and owners must confirm that adequate power is available to run large horsepower pumps, particularly during peak conditions. We have in the past run into the problem of finding pumps with beautiful pump curves being too large in terms of horsepower for the power that was available at the site. The electrical engineer in that situation determined that an electrical substation would have been needed to power them. So that early constraint led to a reevaluation of flow targets with the owner and then looking at other options for pumping strategy. And thankfully, this happened very early on in design, so we were able to troubleshoot and find a different solution. And then the distance between pumps, VFDs, and other electrical equipment also matters, specifically for larger pumps and especially those with VFDs. That combined with long cable runs can sometimes create harmonic and power quality issues, which makes closer placement of electrical components preferable. And then in terms of flows, force main flushing and hydraulic performance should also be evaluated under all operating conditions, not only peak flows, especially if using VFDs, since minimum velocities might not be achieved during low flow periods, and a flushing cycle might be required to ensure solids are properly conveyed to their effluent connection.
When it comes to wet well design, there are several key factors that directly impact performance, constructability, and long-term maintenance. First is sizing and depth. Wet well dimensions are driven by both hydraulic requirements and site constraints, particularly excavation limitations and subsurface conditions. In coastal and southeastern regions, soil and groundwater levels can significantly influence how deep you can reasonably go. Access and maintenance are also critical considerations. This includes evaluating dry pit versus wet pit configurations and how operators will safely access and service equipment over time. There are also established large pump station design guidelines, such as those from Flight and the Hydraulic Institute, which provide a strong foundation for layout, geometry, and operational best practices. From a hydraulic standpoint, minimizing air entrainment and pre-swirl within the wet well is essential to prevent issues like cavitation and reduced pump efficiency. This can be accomplished using elements like vortex suppression cones, ramps, and trough walls as shown in the illustrated designs. And finally, there's also a balance between theory and practice. Design standards provide guidance, but real-world conditions can influence performance in ways that aren't always captured in calculations. The photo here shows a non-structural beam that serves an important hydraulic role as a surface tension brake, facilitating smoother flow into the pumps at high water levels. Unfortunately, we've also found that they serve as effective trash and debris collectors, the inconvenience of which may outweigh the hydraulic advantages. Overall, a well-designed wet well supports both hydraulic efficiency and long-term reliability. Physical modeling can be a valuable tool when designing regional pump stations, particularly when internal hydraulics are uncertain or fall outside of typical design standards. It allows you to observe real flow behavior and validate design assumptions that may not be fully captured through calculations or standard guidelines. Some of the pump station hydraulic improvements I mentioned in the last slide were recommended based on findings from a physical model. The utility was replacing pumps at the station at a rapid rate despite performing O&M best practices. The existing wet well was evaluated, and it was found through use of a physical model that the pumps were experiencing a lot of pre-swirl and cavitation, which was contributing to accelerated impeller and motor wear. Based on the model results, several improvements were recommended, including vortex suppression cones, trough walls, and filleting within the wet well. These changes help slow and stabilize the incoming flow, reduce air entrainment, and improve flow conditions of the water entering the pump volutes. Ultimately, physical modeling helps bridge the gap between theory and real-world performance, giving greater confidence that the station will operate as intended.
Hydraulic modeling is critical to selecting the design criteria for the station, but it's not enough to do the modeling for each individual project. It's important to have a model independent of station projects that accounts for all the basins contributing to the flow at the station under design. An overall system model allows us to analyze how this station impacts others in the system and how it will be affected by system changes. Whether the station's heavily manifolded, subject to terrain-induced high static head, or has shallow contributing gravity sewer systems, making model runs testing the system at current and future flow conditions will help identify key design conditions. Paige and Paulina have discussed the concepts of flexibility in design and redundancy and resiliency. Accurate system modeling allows the design team to account for the variable conditions that regional pump stations experience throughout their life cycle. Starting with a well-developed and verified model is the best foundation for a regional station design. Moving from computer modeling into long-term project planning that those models dictate gives us a couple of targets for project planning for future growth. First, knowing that expected growth and having a reliable utility master plan or municipal master plan are great places to start. These often include planning studies, population projections, and land use mapping. So knowing how the population and the land use will change over time, whether that's residential, commercial, or industrial, whether it'll be built out or a less developed area over time, maybe well-defined now, and how it's changing over the course of time allows us to account for how our station will run over time. Station phasing, how will you accommodate the expected changes to the site and flow conditions, whether that's including space for larger or more pumps, as Paulina and Paige have mentioned, or whether that includes changing operational plans over the long term is critical to your design considerations. Knowing connection points for future flows, if the station will experience increases in flow in the future, and knowing how to account for that, whether that requires larger property or changes to how the site is laid out, is important to that design criteria. And then knowing our limits. How our budget is a critical limiting factor. The space for the station is a critical limiting factor. And as discussed, power supply can also be a critical limiting factor. How those will change based on the expected growth that we find through that utility master plan or municipal master plan leads us to how we plan that future growth at the station.
When working on a station design or station upgrade, whether you're managing the job on the owner's side or you're one of the design engineers, assume you'll be involved in some way with rehabbing the station in 15, 20 years. What can be done today to make your job easier in the future? As some example questions to ask yourself today, are there enough isolation points to bypass flows during rehabilitation? Does it make sense to add in a capped bypass point? A T, valve, and blind flange will be less expensive to install today than cutting in a line stop during future rehabs. If the piping were to be upsized, is there enough room to go up 2 pipe diameters? I've run into this issue a few times, specifically in dry pit stations where valves and piping are located within a building and the rehabilitation scope required upsizing the piping to account for expected new flows. There are already many space constraints when working within an existing building, all of which get exacerbated when valve lay lengths, heights, and general piping footprints increase. Is it beneficial to use more costly but non-corrosive materials today, such as stainless steel pipe or polymer concrete, to save time and money on the back end? This is a great question to ask, especially if corrosion is a main concern at the station. If so, a cost-benefit analysis might be warranted. Is the site in a flood zone or near a water body? If so, should equipment be elevated higher than minimum to account for increased future flood elevations? Is sea level rise a concern if the site is located near a coast? Think through how resilient the stations need to be depending on its geographic location and specific extreme regional conditions. The questions can be scoped to be addressed during the preliminary engineering review phase. And what condition is the upstream collection system in? Can a sanitary sewer evaluation survey be done to determine any structural defects that might be contributing to excessive inflow and infiltration that eventually makes its way to the station? This can save money and effort down the line in rehabbing existing stations, especially those that serve a community that is built out and not expecting continued growth.
As a final thought, plan for things to not go according to plan. Flexibility is definitely key. Flows may increase or decrease, so it's important to design using the best available information today while allowing the station to adapt and remain efficient in the future. Good record keeping is also critical. Maintaining red lines, documenting modifications, and tracking operational observations can provide valuable insight over the life of the station. And finally, developing and maintaining a system-wide hydraulic model is a powerful tool, especially in growing or complex systems. While it requires upfront effort, it provides long-term value for planning and decision-making. Together, these practices help ensure the station remains adaptable, well understood, and effective over time.
Thank you all very much. That was very informative. We really appreciate your time doing that. Your week. Thank you so much.